To understand what a magnet is and how it works, we need to first understand how electrons are structured around an atom. Electrons fill orbitals, which are areas around an atomic nucleus in which electrons are mostly likely to be found. Each orbital can contain up to 2 electrons. They are of opposing spin, so that when they are paired together, they balance each other out in a way that prevents from interacting with magnetic field. Depending on the pattern of filing, an atom may be susceptible to a magnetic field if exposed close enough to one. It is possible to theorize if an atom will have a magnetic properties or not, depending on what's known as the electron filling order. When deciding what orbitals to place electrons in, it is important to start from the lowest energy orbitals first. There are 4 different subshells, S, P, D, and F, listed from lowest energy to greatest. There are also principal energy levels, so a 1s orbital is lower in energy than a 2s orbital. These 4 subshells have 1, 3, 5, and 7 orbitals with them respectively. This is why transition metals are so often magnetic, because they have a d subshell with 5 orbitals that may or not be completely filled with electrons. At this point, it's important to discuss Hund's rule. Hund's rule essentially states that with a subshell of a specific principal energy level, no orbital will receive 2 electrons, which would be its maximum capacity, before all of the orbitals in the subshell receive at least 1. This means that if you have 5 electrons to place amongst the 5 3d orbitals, each of those orbitals will receive 1.5 filled. It is in a situation like this that elements will exhibit magnetic properties. Each electron has a spin and will orient themselves along the magnetic field it's exposed to if it's in an orbital by itself. It is in this case that an atom would be considered to be paramagnetic. As described in the diagram, if an atom has any unpaired electrons in orbitals, it is said to be paramagnetic and susceptible to magnetic field. If an atom has all of its electrons paired up, or rather its orbitals filled, then we will be diamagnetic and not susceptible to a magnetic field. At first glance, to me anyway, this picture may bear striking resemblance to something you'd see at a 1980s science fiction movie. But this is something that is quite common and has been studied extensively here on Earth. This lab explores magnetic properties of metals contained within the particles that make up printer toner. Printer toner is made up of tiny particles of polyester and magnetite, which is a mineral or composed of Fe3O4. It is a mineral, as suggested by its name, that gives printer toner its magnetic properties. In this lab, we suspend the printer toner particles in oil to create a suspension, and then expose the suspension to a strong rare earth magnet, which in this case is a neodymium magnet. The strong magnetic fields generated by the neodymium allows the magnetite particles to align with them, holding them in specific conformations with the suspension of toner and oil. It ends up creating very beautiful and specific structures that are seemingly pointed. Results for this experiment did not work as expected. As you can see from the video, I didn't really get much particle movement, and especially did not get those spiky formations as seen in the introduction video for this experiment. If you look closely, we do see minor movement of toner to the magnet when placed in the upper right position on the screen. I used neodymium magnets that were really difficult to separate, so they seem pretty strong. So I think the reason this didn't work out particularly well is because of the composition of the toner. Most likely, with this brand of toner I used, there just wasn't much metallic particles in it to cause movement with the vegetable oil medium. And this is the video. And I'll play it for the last time. Thank you.